I am very happy to introduce our next speaker, Professor Yves Meyer from Academy of Science. I could talk for a very, very long time about his accomplishments and many prizes he won, but I'm pretty sure you didn't come here to hear me speak, so I'm gonna be very, very short. I'm gonna only mention that he won the Pabel Prize in mathematics and that he's gonna talk today about crystalline measures.
Thank you very much for this kind introduction. I'm very happy and moved and honored to have been invited to this meeting. So I owe so much to Professor Moody. So thanks, Professor Moody, for what you gave me. So the talk will be divided into 4 parts. The beginning is the relation between crystalline measures and the Dirichlet series. And then we'll prove a theorem by Pabel Kurasov and Peter Sarnak, a very nice theorem, a great discovery. And the next topic is sampling and interpolation in the time frequency plane, which is relating crystalline measures to signal processing. And then we'll study the Kepler's problem, where the crystalline measures play a very important role, as was proved by Marina Wiazowska. Okay, so let us begin with Riemann, the Riemann zeta function. So the Riemann zeta function is the sum of the Dirichlet series, sum from 1 to infinity n to the minus s, where the real part of s is larger than 1, and it has a meromorphic continuation with a single pole at s equals 1. So we denote by xi of s the product of zeta of s with the Gauss gamma function at s over 2. And then we can write the functional equation, which is satisfied by the zeta function. And it is nicely written in terms of xi. Xi of 1 minus s is xi of s. And then JeanPierre Kahn and Schoele-Mandelbrot was the uncle of Benoit Mandelbrot, the man of fractals. So they studied more general Dirichlet series. Phi of s is the sum of 1 to infinity c sub j lambda j to the minus s, where c sub j are arbitrary coefficients. When the two following conditions are satisfied, first, lambda 1, lambda 2 goes to is a sequence of positive number that tends to infinity. And B, there is an exponent S naught, a positive exponent S naught, such that the sum from 1 to infinity of absolute value of C sub j, lambda j to the minus S naught converges. Then the Dirichlet series is analytic in the half-plane real of S larger than S naught. And Kahn and Mandelbrot raised the following issue. They wanted to know what are the sequences C sub j, C sub j, lambda sub j, for which phi of S extends to the complex plane as a meromorphic function with a single pole at S equals 1 and satisfying exactly the same functional equation as the Riemann zeta function. So is the Riemann zeta function isolated, or is it a member of a large family of meromorphic functions which satisfies a beautiful functional equation? So I need 3 notations for giving the solution to that problem. The Fourier transform of a function is defined with a 2 pi here, minus 2 pi, y dot x f of x dx. A subset of a set of points in Rn is locally finite if for any compact sets Br, the intersection of E with Br is finite. So it is a sequence of points that tends to infinity in some sense. And the Dirac measure at A, located at the point A, delta sub A, is defined by the fact that the scalar product with a function f is f of A, as everyone knows. So now we can state the theorem by Kahn and Mandelbrot, and it was a long time ago in '58. They proved the following. We consider two properties, and the theorem says that these two properties are almost equivalent ones. The first property is the one which was written before. The function, the Dirichlet series phi of s extends to the complex plane as a meromorphic function with single pole at s equals 1. Moreover, phi satisfies exactly the same functional equation as the Riemann zeta function. And property 2 is completely distinct. It says that there exists a constant C naught, there is no C naught in the definition of phi, such that the atomic measure mu equals C naught Dirac mass at 0 plus the sum from 1 to infinity C sub j delta lambda j plus delta the Dirac mass at minus lambda j. So these atomic measures satisfy the fact that its Fourier transform equals mu. Mu hat equals mu. The C naught, which does not show up in the first statement, is just the residue of phi at s equals 1. So you have a single pole, you have a residue, and this residue is C naught. So that's a byproduct of the proof. Then these two persons, Kahn and Mandelbrot, prove that 2 always implies 1, and that implication was already known by Riemann, and Kahn and Mandelbrot in their paper acknowledge the fact that this was proved by Riemann. So 2 implies 1, and conversely, 1 implies 2 under a strong condition. The condition is rather strong. It says that you have large pieces of these lambda j, which are which satisfies the relation lambda sub j plus 1 minus some lambda j larger than a beta, which is strictly positive for a large intervals of j. And we'll see that this condition is strong, and there are many examples where it is not going to be satisfied. Nevertheless, that was the theorem they proved. And in their paper, which is very interesting, in their paper, they did not provide any new example of a measure satisfying this condition. We'll see what are the known examples, and Kahn and Mandelbrot. So this leads us to a definition of a crystalline measure. A crystalline measure is an atomic measure on Rn such that 1, mu is supported by a locally finite set. 2, mu is a temperate distribution. That means that you can compute the Fourier transform. And 3, the distribution of Fourier transform mu hat of mu is also an atomic measure supported by a locally finite set. A very important point is that in general, mu is not translation bounded. So mu can have a polynomial growth at infinity in a sense which is easy to be given a more precise definition. So in general, mu is not a translation bounded measure. So we relate that with a talk by Professor Daniel Lenz from Jena. So if mu is a crystalline measure, by definition, we have an identity saying that mu is a sum of Dirac masses, and at the same time, it is the inverse Fourier transform of its Fourier transform. So it is a sum of exponential, of vibrating exponentials. And the right-hand side, the last series converge in the distribution sense. The convergence of the first one is obvious since the sequence of points lambda is locally finite. So there is no issue in the convergence of the first series. And of course, the convergence of the second one is in distribution sense. Therefore, mu, as it was pointed by Professor Lenz, mu is a simple geometric object given by the first series, which is a sum of its Fourier series expansion. So it is not given by a Fourier integral, but a Fourier series. This would be the case if mu was a periodic or an almost periodic distribution. In all the examples which will be given, mu is an almost periodic distribution. Okay. And a well-known example is Dirac-Combes. So let me, the Dirac-Combes is a usual sum of Dirac masses on a lattice. So it is periodic, and in that case, we have mu hat equals mu. So what was observed by Riemann himself is that the fact that the Dirac-Combes satisfies this property implies the functional equation for the zeta function. Riemann did not speak in terms of measure, of atomic measure, but in equivalent terms, in terms of the Poisson summation formula. So he derived the functional equation from the Poisson summation formula, which is equivalent to saying that the Dirac-Combes satisfies this functional equation. So conjecture, the first problem I would like to ask, a crystalline measure, I believe strongly that a crystalline measure is an almost periodic distribution. An almost periodic distribution means that for any test function phi, the convolution product is an almost a Bohr or almost periodic function. So the Guinan crystalline measure, which is whose definition is given later on, is not an almost periodic measure, but is an almost periodic distribution. So let us return to Dirac-Combes. So the simplest example of a crystalline measure is the Dirac-Combes. We have mu hat equals mu, which can be rewritten in terms of the Poisson summation formula. And it is from the Poisson summation formula that Riemann derived the functional equation. We need a definition to better understand the example which will be given later on. So we consider a Dirac-Combes supported by a coset of a lattice, gamma sub j in Rn, and we move that by x sub j. So we take this Dirac-Combes, we move it by xj. We call f sub j a finite set, and we consider a finite sequence of trigonometric polynomials, and we multiply sigma j by g sub j. Then, so we have constructed capital N measures supported by cosets of lattices, and then the sum of this measure is a general Dirac-Combes. So this definition is interesting because the Fourier transform of a general Dirac-Kamb is a generalized Dirac-Kamb. That's trivial. Therefore, a generalized Dirac-Kamb is a crystalline measure because a lattice is locally finite. So, are there other crystalline measures? So, Kahn and Mandelbrot were unable to give other examples. All the examples of the crystalline measures they gave in their paper are a generalized Dirac-Kamb in such a way that the zeta function, the Dirichlet series, which were related to these measures, to these crystalline measures, were in fact belonged to the family of the Riemann zeta function. So there were just some manipulations on the Riemann zeta function. So the first one who was able to give a very, very interesting other example is Andrieux Guinan. I am fond of Andrieux Guinan because he was a very interesting person. He was a student of Hardy. He was born in Australia, and he got a scholarship for getting a PhD at Cambridge, and he was a student of Hardy, and he spent all his life working on the Riemann hypothesis. And he wrote a beautiful paper in 1958, exactly the same year as the paper by Kahn and Mandelbrot, in Acta Mathematica. And he proposed the following. So the paper is on crystalline measures. So it is devoted to crystalline measures. And he gave a beautiful example. So you define a sequence, and then after winning the war, he was an officer in the Royal Air Force. So he participated to the Second World War, many missions, and then he moved to Canada. And he played a very important role in building the mathematical school in Canada, Andrieux Guinan. And so you define a sequence gamma k of rational numbers, a sequence of rational numbers by this identity. So it is related to automorphic forms. So you take the product from 1 to infinity of 1 minus q to the n, 1 plus q to the 2n to the 2/3 power times 1 plus qn to the 1/3, where q is a complex number with inside the unit disk. And of course, it converges beautifully, so it is a Taylor expansion and gamma k of the coefficient. Gamma 0 is 1, then you have rational numbers. And the only puzzling problem is to prove the estimate of a graph estimate on gamma k. The absolute value of gamma k is less than c times k to the 1/3. Now, lambda k is the square root of k plus 1/9. K is 0, 1, and so on. And the Guinan atomic measure is the sum from 0 to infinity of gamma k, delta lambda k, plus delta minus lambda k. So there is no Dirac mass at 0, because lambda 0 is not 0, it is 1/3. And the Guinan zeta function is the following. It is exactly like in the paper by Kahn and Mandelbrot. It is the sum from 0 to infinity of gamma k, k plus 1/9 to the minus s/2. It converges if the real part of s is larger than 8/3. And then we have the following. So it is a joint paper with Guinan, and I will tell you the story afterwards. The theorem says that the Guinan measure satisfies mu hat equals mu, and it follows by the proof given by Riemann that the Giguere function, the Giguere zeta function, is an entire function in the complex plane. And it satisfies exactly the same equation as the Riemann zeta function. So you have exactly the same equation. So the Giguere zeta function is a fair companion of the Riemann zeta function. Okay. So the story is the following. Alexander Olewski drove me to the paper by Guinan. So I got the information of the existence of the paper by Guinan by Alexander Olewski. And Alexander Olewski, who had read the paper, told me that the proof by Guinan was incorrect. There was no proof, just a series of calculations, and the proof was a kind of guess leading to a proof. And I could complete the proof by Guinan, so Guinan was absolutely right. And the only thing which was, so it was too early after the definition of distributions by Laurent Schwartz, and Guinan did not understand that for proving his theorem, he needed an estimate on gamma k. And my only contribution was to prove the estimate on gamma k. Then everything converges in the distribution sense, and we could finish the proof by Guinan. So now the second topic. The second topic is a beautiful theorem, a theorem I admire very much, by Pabel Kurasov and Peter Sarnak. They prove the following theorem, which is spectacular. So they prove that there exists a uniformly discrete set of real numbers, lambda, such that the vector space over the rational generated by lambda is infinite dimensional. And then the measure, which is the simplest measure carried by lambda, the sum of the Dirac masses over lambda without any coefficient, is a crystalline measure. So it is extraordinary because it means that there exists something like a Dirac comb, but on a support which has no arithmetic structure, or a very hidden arithmetic structure. So it is a new family of aperiodic orders. So that explains why this theorem is so important. So it was proved two years ago. So for proving one, you need a theorem by Pierre Liardet, who was a number theorist. I will not insist on that because the application of the theorem is straightforward. And let me mention that the atomic measure mu sub lambda is, in that case, an almost periodic measure. In the most precise sense, that means that the convolution product with any compactly supported continuous function is a Bohr almost periodic function. It is not true that the Fourier transform is an almost periodic measure. It is false. So it is mu, which is almost periodic. Let me mention that the Fourier transform of mu sub lambda has a much more complicated structure. It is not a sum over the dual set, capital F, of Dirac masses. You need some coefficients on the Fourier transform side. And the Fourier transform of mu sub lambda is not almost periodic. But this idea, this hint, will lead us to a proof, a geometrical proof, and we are going to construct mu sub lambda by constructing first the compactification of mu sub. And the theory is beautiful. The compactification of mu sub lambda is an Aheron measure. and higher measures are related to inner functions. So here we enter the country of several complex variables. So it is related to several complex variables. So let me explain what is a higher measure. So T is a multiplicative group of complex numbers of modulus 1. And the other T's are over Z. So of course, they are isomorphic. D is the open unit disk of the complex plane, and Dn is a polydisk. Then the n-dimensional torus, Tn, is the distinguished boundary of Dn. A distribution S on Tn, on the torus, is holomorphic if and only if it is a trace on Tn of an holomorphic function on Dn. And we pass to the limit as we approach the distinguished boundary. The distinguished boundary means that Tn is not the usual boundary as a point set topology. It is just a tiny part of the boundary, but the knowledge of an holomorphic function on the distinguished boundary suffices to construct the function inside. So it is a set of uniqueness in that. Okay, we are going to assume that the n is larger than or equal to 2. And now we arrive to the definition. A real valued radon measure on Tn is an Ahern measure if it is the real part of a holomorphic distribution on Tn. So we'll see what it means in more concrete terms. So now we quote Ahern. Ahern proposed the following definition, which is exactly what I said before. A real Borel measure on Tn is a Ahern measure. Ahern did not say Ahern measure, he gave another name. If the Fourier coefficients of mu are 0, whenever not all the key subjects have the same sign. So it is different from 0 only in 2 cases. All K subjects are non-negative, or all K subjects are non-positive. So the two sextants. And in all other cases, the Fourier coefficient vanishes. So there are very few locations where the Fourier coefficient do not vanish. The Ahern measures are the measures whose Poisson integrals are the real parts of holomorphic function. So now I am going to prove the theorem by Kurasov and Sarnak, and it will give the definition of curved model sets, of a generalization of model sets. So we assume that n is larger than or equal to 2. We let alpha 1, alpha n be n positive real numbers. We assume that these numbers are linearly independent over Q. And we map the real line in an irrational way on Tn by just mapping T to alpha 1T, alpha nt. Now, the real line is a dense subgroup of T sub Tn. So now we defined curved model sets, which is a very important definition. So V now is the graph is contained in Tn, and it is a graph of a C1 function from Tn minus 1 to T. So it is just a smooth graph, and H is as before. So we say that alpha 1, alpha n is transverse to V, and that usual definition of differential geometry. If there exists a beta strictly positive such that the vector alpha, the vector alpha 1, alpha n, when it hits V, is not tangent, is transverse to V, and it is given by this relation. So this relation should be satisfied for at every point of Tn minus 1. So the argument is in phi. And of course, we have just alpha 1, alpha n minus 1, because T has disappeared because we are just on the differential picture. Then the curved model set, if this transversality condition is satisfied, the curved model set lambda V is defined just as was defined a model set, but in a model set, V was a piece of an affine plane, hyperplane. V was a compact piece of an affine hyperplane. Here, V is a curved manifold, and the curved model set is a set of points T in R such that H of T belongs to V. And now we have the beautiful theorem. If the vector alpha is transverse to V, then lambda V is uniformly discrete. That is trivial. But the interesting part of the theorem is that if alpha 1, alpha n are positive, and if the smooth measure mu on V is a higher-end measure, so we need to build a measure mu on V, which is a higher-end measure, then mu composed with H, we should define that, is a crystalline measure supported by lambda. So that's a recipe for constructing crystalline measures supported by curved model sets. And now we have to fix the smooth measure on V such that it is a higher-end measure, and we need to compute its Fourier coefficient. So here is the construction of the measure on V. So phi, as before, is a C1 function. V is a graph of phi, and mu is the image measure of the higher measure on Tn minus 1 by the mapping capital phi, which sends x prime to x prime phi of x prime. Because V is a graph, then this image measure is supported by V. And we have the following theorem that mu is a higher-end measure if and only if exponential of minus 2 pi I phi is a inner function. So it relates all the construction to the fact there are many inner functions. So inner functions, we have trivial examples. If n equals 2, n minus 1 is 1. And for phi, you just take a Blaschke product and you have infinitely many curved model sets and crystalline measures just indexed by Blaschke products, but you can do the construction in any dimension. So this proof is interesting because it gives a geometrical interpretation. The proof by Kurasov and Sarnak was completely distinct. The first proof by Pabel Kurasov was based on his theory of quantum graphs. So in a remarkable series of papers, Pabel Kurasov did PDEs on quantum graphs, the Schrödinger equation, quantum graphs, and so on, and using ideas similar to the trace the Selberg trace formula or the Holland-Verdier trace formula on manifolds, he could prove using these ideas the existence of crystalline measures. So crystalline measures seem to appear in many places in mathematics. So now we relate that to signal processing. So the restriction of a function to a set is denoted by f restricted to it. We start with the following definition. We are given two locally finite sets. We say that lambda f is a pair of uniqueness if the following property satisfies. You take any function belonging to the Schwarz class, and we assume that f restricted to lambda equals 0. Just a few zeros, because lambda is a set of points tending to infinity. You assume that the Fourier transform of f restricted to f is 0. That forces f to be 0. The only possibility is that f vanishes. Of course, the knowledge of if lambda is any closed set, the knowledge of a Schwarz function on lambda does not suffice to retrieve f, because f can be arbitrary on the open set, which is a complement of lambda. This lack of knowledge is compensated by the information given by the Fourier transform on f. So this is, as we'll see, a very important problem. Let us comment the definition. If lambda f is a pair of uniqueness, then any Schwarz function is uniquely defined by its restriction to lambda and by the restriction of its Fourier transform to f. Now we are going to assume a property which is satisfied in all the examples we will study. We assume that the points in lambda are not too dense. That means if you restrict to a ball of radius j, the number of points in that ball has a polynomial growth, when capital N is in general much larger than the dimension Hn. And that the distance between these points exceeds c to the j minus m for some exponent. That implies that we know exactly the restriction to lambda of the Schwarz function. It is exactly the space of sequences indexed by lambda which have a fast decay at infinity. The same assumptions are imposed to f in the following conjecture. And we'll see an example where it is satisfied. If lambda f is a pair of uniqueness, there exists an exponent n, which can be much larger than the preceding one, with the following property. For any Schwarz function and every point, there exist two sequences, c lambda x naught and a y x naught, indexed by lambda and f, such that this function f can be reconstructed by its restriction to lambda, by this linear formula, and by the restriction of the Fourier transform of f on capital F. And we have this growth condition, polynomial growth, on the coefficients, so that everything converges beautifully. The corollary of this conjecture is that for every x naught in Rn, the atomic measure, which is delta x naught minus the sum over lambda, c lambda x naught d delta lambda, is a crystalline measure. So if you can solve this problem, you have infinitely many crystalline measures. And this is if and only if. And now we arrive to Ukraine, which is something which is so frightening and so with such anxiety, with the beautiful work of Marina Wiazowska. She proves the conjecture. It is a joint paper with Danilo Radchenko. So the theorem. So we assume that lambda is plus, we are in one real variable, and lambda is plus or minus 1 square root of k. And capital F is the same set. And she proves the following theorem. There exists a sequence ak of x of even real-valued Schwarz functions in the real variable x with the property that for any even Schwarz function f and any real number x, we have the following identity. So we have a universal identity which allows to compute any Schwarz function from the value of the set of square roots and the values of the Fourier transform of the set of square roots. So it is something as important as the theorem by Fourier that a function is a sum of Fourier series. And the right hand side converges uniformly to F and also in the distributions. So everything can be computed. In her paper, she has an explicit formula for ak of x and for the Fourier transform. So the formula is completely balanced because the second series, you put Fourier transform everywhere. And of course, if you have such a series, it can be proved that it has this special form. This cannot be true if f is odd. It is very amusing. Indeed, if you take the function sine pi x squared divided by hyperbolic sine of pi x, this is a Schwarz function because sine has an exponential, hyperbolic sine has an exponential growth at infinity. G vanishes on plus or minus square root of k, and the Fourier transform of this function g is minus ig. It is so beautiful. And now we return to crystalline measure. Let x naught be a real number, then the measure, the atomic measure, which is delta of x naught per delta minus x naught, minus sum of 0 to infinity, ak of x naught, the delta at square root of k plus delta minus square root of k is a crystalline measure whose Fourier transform is given by that. So what is very striking and beautiful here is the similarity between these crystalline measure and the one proposed by Andrew Guinan. In Andrew Guinan's work, instead of square root of k, you add square root of k plus 1 over 9. And this similarity can be explained, beautifully explained, by using the theory of automorphic forms, algebraic geometry. So that's a work in progress. So the connection is not accidental, you know. Now we apply, we follow Marina Wiazowska, and we study the problem of Kepler. And we see that crystalline measures are hidden in the problem by Kepler. Kepler raised the following issue. What is optimal in terms of density packing of the ordinary space with balls with radius 1. And this problem can be raised in any dimension. So that's an illustration of the solution in R3. So Marina Wiazowska discovered the optimal sphere packing in dimensions 8 and 24. So the starting point of her work was the linear programming approach by Kahn and Elkies. So that's the theorem by Kahn and Elkies. So you'll see immediately the link with the preceding section. Let phi be a real valued function belonging to the Schwarz class. And it will be a very special function. Let us assume that there exists a beta strictly positive, such that we have the following property. Phi of 0 equals the Fourier transform of phi of 0, which is the integral of phi, equals 1. Phi of x is non-positive when the length of x, the Euclidean length of s, is larger than beta. And the Fourier transform of phi is positive, non-negative everywhere. If you can catch such a function phi, you have immediately an upper bound of the density of a collection of disjoint balls of Rn. This density cannot exceed pi to the power n over 2 divided by gamma n over 2 plus 1 multiplied by beta over 2 to the n. A very important observation is that without losing generality, phi can be assumed to be radial. Because if you have a function phi with these properties, you just average on rotation of phi, and you have another one which satisfies all these properties and which is radial. So we focus in this presentation on dimension 8. So the lambda 8 lattice, a beautiful lattice, is defined by as a set of points in Z8 union is Z plus 1/2 plus a half to the 8. So either they are all integers or they are all shifted by one integer shifted by 1/2, the coordinates. And then you assume that the sum of these coordinates is an even integer. So that's a lattice, you play with the definition and you satisfy. The beauty is that the dual lattice of lambda 8 is lambda 8. And you have the Poisson formula. And what Wiazowska proved is that the optimal packing in dimension 8 is achieved with balls of radius square root of 2, half square root of 2, centered at the point of the lattice. And these balls, they are pairwise disjoints except the boundary points. So it is very easy to check that the distance between 2 points of the lambda 8 lattice is larger than or equal to square root of 2. And it implies that these balls of radius square root of 2 divided by 2 are disjoint. So now here is a beautiful story. So Wiazowska used the linear programming theorem with the value beta equals square root of 2. And now we are looking for the function phi. We are guessing how to construct the function phi. Because the function phi should be negative outside the ball of radius beta, we obtain that the sum over the lattice, and since phi of 0 is 0, the sum over the lattice of phi of lambda is 1 minus a, where a is non-negative. Now, since phi hat is everywhere non-negative, the sum of phi hat on the dual lattice, which is the same lattice, is 1 plus b, where b is non-negative. And the Poisson formula identity yields that 1 minus a equals 1 plus b, and that forces a and b to be 0. Therefore, phi and its Fourier transform vanish on the lattice, except at the origin. Since phi is a radial function, phi and its Fourier transform vanish on every sphere Sm centered at 0 with radius the square root of 2m. Because such sphere contain a point in the lambda 8 lattice. And now we observe that we have the same problem of constructing a function phi by imposing the value of the function phi on a set of points of the set of square root of plus or minus 1, the square root of 2m, and the restriction of the Fourier transform to the same set. So this problem is not identical to the problem which has been solved by Marina Wiazowska in the preceding section, but has exactly the same flavor. And that was the intuition of Marina Wiazowska. So she used the same tools for solving this problem. Using this observation, Wiazowska could construct a Schwarz function satisfying the condition of the Kohn and Elki's theorem. Then the story ends that way. So by applying the linear programming theorem, she obtained that the density of any collection of Dijon balls with radius r in R8 cannot exceed p to the 4 over 384. That's the number given by the linear programming theorem. But a direct calculation shows that p to the 4 over 384 is the density of the collection of balls with exactly this radius. So the density cannot exceed this number, but you have already the lambda 8 lattice which gives this number. So that completes the proof. So now there is an amusing point. There are exactly 240 spheres S of G of radius square root over half square root of 2, centered at this point, which are tangent to the sphere of radius square root of 2 over 2 centered at the 0. And these local configurations, so just the spheres that touch the sphere centered at 0, is optimal since this number is a kissing number in dimension 8. It is the largest number of Dijon balls of radius r which are tangent to a given ball of radius r. So the optimal configuration is locally optimal and it is related to the kissing number. So thank you very much for your kind attention.